A battery with an EMF of 12 volts and an internal resistance of 0.2 ohms are connected in series to a very small electric motor. This is the same battery we've just been dealing with, and a resistor T of unknown resistance as shown in the circuit on the next slide. The motor is rated X watts. Okay, that tells you the rate at which it can use energy to give or convert energy from electrical to mechanical. And it's also rated 3 volts and operates at optimal conditions. And what that means is that it is operating at 3 volts and it is putting out X watts of power, in other words, X joules per second. Okay, and it's running at peak or optimal conditions. When the switch S is closed over there, find out the value of X. The value of X is going to be the power output of the motor. Okay, the power of the motor. All right. Now, let's go on to the next slide. The average power is going to be equal to the force multiplied by the average velocity, because this is lifting something, and that is going to be equal to the force that it has to exert, which is the mass that's hanging on there, mg times the V average. Okay, and the mass is 0.35 kilograms, and G is 9.8, and the velocity is 0.4, and that's equal to 1.37 watts, and that is the average power output when that little motor, working at optimal conditions, lifts and does the work that we have described over here. So it's 1.37 watts, and that is the value of X. I guess the other way we could have done this, and I know there are usually many ways of doing these things, power is equal to the work of the non-conservative forces over delta T, and that is going to be the kinetic energy plus the potential energy over delta T, and that is going to be, well, when we've lifted the thing right up, it's got no more kinetic energy, but it's a mass of 0.35, which has been lifted up from 0.4 from 0, and we multiply that by 9.8, and again we're going to get 1.37 watts. So you could have done it that way as well. All right. And sorry, it's per unit time, so I would have divided that by 1.